I mean, like, certainly there is a whole Southern hospitality, but I'm not, I don't know. Ma'am tends to be for people with gray hair. I mean, some people are like, oh, if you're married, but other people are just like, if you're in any sort of position of authority. And for his job, I would default calling everybody ma'am or sir. Because some people are so like, I have a doctorate. You should call me doctor. I'm like, all right, well, we already know where you stuck your doctor. And like, it is a big deal, but it's not like a everybody absolutely should call you doctor and must know you're a doctor big deal. Whew, okay. So I am still trying to finish grading my pre-cal. So I will be grading y'all maybe Sunday night. It might take me till Monday though. So probably looking at Wednesday for giving it back. But I will try to get the extra credit points in sooner rather than later. Okay. Sorry, I did a lot already today. My brain's a little woo. I did finally get the video posted, but it was being really annoying, so I had to do it as a Panopto link. Um, so when you click the link, it should load Panopto like in a new tab, and then it'll load the video if you want to watch the video for last class. I think it was like the tiniest bit too big, and that's why Canvas was being stupid. All right. So now we're getting back to our maxima and minima, the highs and the lows. So what we have here, our directions are find the critical points of the function on the interior. It should say of its domain. Okay. So part of this is understanding what the domain of this thing is. So there's three main cases when our domain has potential problems. The first classic is whenever we have something that's on the bottom, we have to make sure to say that thing can't be zero. So I stole this from Chris's notes. He writes it as a face. So if the face is on the bottom, can't be zero. If the face is in a square root, has to be greater than or equal to zero. If the face is inside a log, so anything inside a log function, any type of log, it has to be strictly greater than zero. So here, since we have 2x squared times natural log of 3x, that domain restriction is going to apply. Boy, that is a very sad happy birthday. Okay, that's better. So domain. 3x is greater than 0, so x is greater than 0. 0. So our domain is from 0 to infinity, but we can't use 0 itself. So the reason it says the interior of the domain is like if 0 actually was a number and it was inclusive with a bracket, saying interior means we're still going to ignore the endpoints. But that's all interior means. It just means ignore endpoints. Now our function here though is a product. This is 2x squared times the natural log of 3x. So we're going to have to use the product rule to find our first derivative and then to set it equal to 0. And in doing that, the product is going to give us some interesting things. So it is possible when we're solving that to get values that aren't actually usable in the original function. Like sometimes that just happens with derivatives. So we're going to keep an eye out on that. But I have f of x. So we're going to start. We'll go df dx. And now I have that 2x squared times natural log of 3x. So we're doing derivative with respect to x of 2x squared times ln of 3x. That's how I do my ln's. It's capital L. It is absolutely not an I, despite what my pre-cal students think. Yeah, that's what I thought. All right, so we got a product rule going on. So I'll go ahead and call this 2x squared A, this ln of 3x B. So when we're doing our derivative, df dx, we take the derivative of 1, so a prime times b plus a times b prime. So the derivative of 2x squared, the 2 is a constant, so it's just going to carry over. Then the derivative of x squared becomes 2x to the 2 minus 1, which is 1. And then this will be times b itself, ln of 3x, plus, now we keep the 2x squared, and we're going to do times the derivative of the natural log of 3x. So when we do the derivative of a natural log, what happens? Yep, so we got 1 over whatever's inside, which is our 3x. And then our chain rule says times the derivative of the inside. So what's the derivative of 3x? Yep, just 3. But I'll go ahead and write it like this, just so it's clear why we're getting a 3 there. df dx is 4x times the natural log of 3x plus, a little more interesting, our x's cancel. So we have momentarily 2/3 times x, but our derivative of 3x is times 3. So this is actually just going to be 2x. Make notes a little different. All right, we're finding critical points. So now I want to know, when is the derivative 0? So I'm putting a 0 in place of df dx. And if we look at this, we can see they both have an x. They actually both have a 2x. So that's going to leave me with 2 times the natural log of 3x plus 1. All right. Anytime a product is equal to 0, we can split the product, each piece. So either 2x equals 0, which is really just telling us x equals 0. That's a potential critical value. Or the very ridiculous 2 times the natural log of 3x plus 1 equals 0. Which if I start solving, I'd have the natural log of 3x equals -1/2. Okay. And for a second, I was like, and then this is impossible. I was like, wait, no, it's not. I can have a log equal a negative number. I just can't put a negative number inside the log. Nope, we can keep going. So natural log is defined to be the inverse of what? So we're going to use our inverse function, e, and apply that to both sides. So it's e to the. So on the left, the e to the and the natural log of cancel each other out. So now we just have 3x on the line, and then e to the -1/2, which is something I can type on a calculator, so it's some number. And then last step, we divide by 3. So x equals 1/3 e to the -1/2. So we have a critical value. We don't know if it's a high or a low. Because this whole process was setting the derivative equal to 0 to figure out where the graph either has a peak or a valley. Yep. So we got to test that. X equals e2 minus 1/2. So I need to know what the function value is for that in the original function, which is ugly. So it will be, let me do it this way. Two 1/3 e to the negative 1/2 squared times the natural log of 3 times, that looks like a2 there. 3 times 1/3 e to the negative 1/2. So the 3 and the 1/3 cancel, then the ln and the e cancel. So this thing is actually just going to be negative 1/2. This one though is ugly though. We get 2/9 times e to the negative 1 times negative 1/2. So negative 1/9e. You don't have to simplify it with the e's. Like you could totally get the decimal for the 1/3 e to the negative 1/2 and just plug the decimal in and crunch it up and get the number. Like this is just me playing around with numbers and being silly. So f of all right. Now we did get x equals 0, but I ignored that because our domain was restricted from 0 to infinity. Now, the number decimal itself we got, the 1/3 e to the negative 1/2, that is still a positive number. So this is about 0.202. So before that x value, the graph is going a particular direction. Either it's going down or going up. And then after that value, it's either going down or going up. But it's hard to tell like what's going on in this graph when we only have one critical number to test. So like I've got this negative 0.0408. And based on, oh, just based on the equation 2x squared, as I plug in really big numbers, that's going to get really big. And then the natural log of 3 times a big number is also going to be a large positive number. So the right side of this graph should shoot off to infinity. Boop, boop. Awesome, thank you. And it's okay to just leave that in here, right?
Yes, okay, okay.
Cool.
Okay.
You too. He didn't call me ma'am that time. All right, so I'm actually going to assume that this is going to be a minimum because just my basic knowledge of the graph says it's going to shoot off to infinity. But honestly, I want to check and make sure because I'm really not 100% sure what this graph would look like. So Desmos is an excellent graphing calculator. So y equals 2x squared ln open parentheses 3x, close it. Let me flip the share. All right, so when I click like on the line, you can actually see it highlights some points. So we can see here that 0.202 and the negative 0.04. Like those are the two decimals we found, and that is a low point. The 0 should not be filled in. What? No, if it's filled in, it means it's a point on the graph. Like they're putting it like it's a point on the graph, but it's not on the graph. But that's one of the flaws with most graphing utilities. They don't have a way to show an open circle. So you have to know that circle is open. Ah, yes. All right, so the first one was showing me where I am. So if I was doing a limit at that point, the point isn't on the graph, but the limit from the right would exist and it would equal 0. But when I drag the point on there and hold it, then it shows me that open circle. Thank you. But if I move it, then you can see it fills in. So open, filled in. Yeah, it's just because it was labeling it as a location, not necessarily a point on the graph, whereas the other ones here are absolutely on the graph. Ooh. All right, let's flip the share back. So you can, especially if you're getting flustered about like, where is this point? Is it going to be a high or a low? Like, what's going on? Absolutely, take a look at it in Desmos. It's a really fantastic graphing utility. And anywhere except a math classroom, you can use all your resources. It's just a math classroom where we're annoying. All right, so this is an absolute min. But it's also good if you've got like several functions and you're trying to figure out like how they all intersect and look. Throw them all in Desmos. It'll plot them all for you. And it's a lot more user-friendly than graphing calculator because you can actually zoom. Mostly it's just about making sure that what you type is what you wanted to see. So this is going to sound like a stupid answer. It's an excellent question though. On the exam, how are we supposed to tell if it's a max or a min? So right now, we haven't covered the first or second derivative test yet. But when we cover those, like one of the ways is to take the second derivative, plug in the x value and see if you get a plus or a minus. But the other way is with the first derivative test, we'd create a number line and then we'd test a number to the left and to the right of the 0.202. So if the number to the left gave us positive, that means that it's increasing there. If the number to the left gave us a negative, that means it's decreasing. So we are going to have later tests that'll help us answer this question without a picture. But I always hated it when teachers were like, well, you'll figure it out later. It's like we kind of have that information now, we just haven't formalized like the actual like way we do it. That should be coming. I don't remember if it's next class or the class after, but we are going to learn it very soon. So now we have find the absolute maximum minimum values of this ugly function on the interval. Now this is when we ask absolute max and min, this is how we typically ask it on a test. We give you endpoints. So that way you don't have this awkward, like, is it the low? Is it the high? Because you've got endpoints to test it against. And you're literally just saying, all right, who's got the highest Y value? Who's got the lowest Y value? Done. So for our test values, we already know for sure that we are going to test -1/2 and 2. Now we got to take the derivative and see if there's any other numbers in there. And like just looking at the function, if I plug in 0, I'm going to get a 0 back out. Odds are 0 is going to be one of our critical values. That doesn't necessarily mean it'll be a max or a min, but sometimes it is. All right, so f of x is x squared minus 3 times x to the 2/3. So f prime of x, or df dx if you want to write it that way, either way is fine. Derivative of x squared is 2 times x minus 3 times. We have another power rule, it just looks ugly. So power is 2/3, I bring the power down. 2/3 times x to the 2/3 minus 1. So I'm going to go ahead and write it in there. That is the kind of thing, though, you can absolutely punch that on your calculator, get it to spit out the answer. But 2/3 of a thing minus a whole thing is going to put us in the negatives. And it'll be -1/3. So 2x minus the 3's cancel there, so it'll be 2 times x to the -1/3. Now the fun part is figuring out how to solve this. So please stop. Critical values happen when the derivative is 0 or when the derivative is undefined. I'm going to rewrite this so it's 2 over x to the 1/3. So as a fraction, what value would make this undefined? What number are we not allowed to divide by?
0.
Yes, 0. Ah, sorry, I missed you typed it in there too. All right, so because of the fraction here, x cannot be 0, so 0 is a critical value. Because just anytime we're dividing by something with a variable, it's what would make that whole thing on the bottom equal 0. And in this case, it's just x to a power, so 0 to any power is 0. All right, so 0 is going on our list. And now we have this awkward, like, is there something that would make this equation equal to 0? So if I do plug in the 0 here, We're gonna do something weird. I'm gonna multiply by x to the 1/3. But the reason it's weird is we typically don't multiply by expressions with variables because you could be multiplying both sides by 0. That would still keep the equation true. It just like kind of complicates things. But here we've already said, well, x can't be 0. Like we've already like taken that as a value, so it's kind of okay to multiply by it. I mean, on this side, it's still just going to be a 0, but 2x times x to the 1/3 minus 2 now. So I can add the 2 to the other side. So I have 2 equals 2 x to the first times x to the 1/3. These guys are next door neighbors, so it's a positive relationship. So that will be x to the 4/3. Now we divide by 2. So now I have x to the 4/3 equals 1. So a base raised to a power is equal to 1. That happens when x is 1, or sometimes when x is -1. So I'm going to take it a step at a time. First, I'm going to get rid of the third power, like the 4/3 fraction by raising it to the third power. So I have 1 equals x to the 4th. And now I would use the 4th root. And because this is an even index root, like a square root, it gets a plus or minus. So we actually have x equals 1 or x equals -1. So those are more critical values. So the x equals +1, sure. But remember, our interval is also our endpoints. -1 is actually further left than -1/2, so we're not going to use that.
And it's up to depending on what the endpoints are, right? Okay. So in this case, would be the bottom.
Yes. All right, so now we are just going to be testing. Now remember, we're going to see what the y values are in the original function. So the 0 was undefined in the derivative. That doesn't mean it'll be undefined in the original function. A lot of times that is the case, but in this one, it actually works out. Like when we plug in 0, we get 0. When we plug in 1, we get 1 squared minus 3 times 1. So we get -2. That might be low. Plugging in 2 squared minus 3 times 2 to the 2/3. 2 or 4 does not cube root nicely, so that is an ugly decimal. So 4 minus 3 times 2 to the 2 divided by 3. Right. -0.76. And now plugging in the -1/2, that's just going to be ugly, period. So -0.5 squared minus 3 times -0.5 raised to the 2/3. Okay. So some calculators, like basically, when you raise -1/2 to the 2/3, I don't know why I was giving me shit. Negatives are fine in a third root. Sometimes the calculator doesn't like the fractional power, so you have to split it up into a squared and a 1/3 power. The regular calculators will probably handle it fine. This is really more because my phone is stupid. All right, so looks like strangely enough, 0, 0 is actually the high point. Then our absolute min is -2. And that is at x equals 1. Now, like here to the end of the chapter, the name of the game on almost everything is going to be take the derivative, set it equal to 0. Sometimes it'll be, and then take the derivative again and set it equal to 0. So this whole finding critical values, we're going to do quite a lot. We are going to start looking at functions that aren't quite so ugly, because we're actually going to talk about what does this graph look like. And when we do that, we usually are looking at polynomials. Sometimes it'll be rational functions. And then the last slide is just the summary slide. So anytime you're doing absolutes, check the endpoints, find your critical points, plug them all back into the original function, find your high and your low. And then make sure when you're answering it that you're filling in the correct number in the correct spot. So now my question for y'all, because we still got 13 minutes, is there a question on the web work that you guys would like to see worked out? Right here, let me flip the share just to give you guys like the preview look, but then I'll flip over to 5 since you're asking about it in particular. Because on most of these, one is as good as another. All right, so this one is an actual graph. You can see the endpoints, they're filled in, and you can see the low value is occurring at x equals 1, but the value itself, actually, hold on. Yeah. If you tap on the graph, it opens up in a bigger picture and the numbers are much easier to read. So it looks like -18 is the min and 0 is the max. Yeah. All right, so let's just quick look, another graph. Open circle though, so we're not going to get a max on that one. Open circle on the bottom, so no min. That is a horrible graph. Like seriously, how would you pick the minimum? I mean, it's like at -3.5, but what is it? I don't know. -0.1 maybe, -0.2. And then our high, 1, 2, 3.2. This is a shitty question. Okay. So same kind of thing, but I'll wager the graph is kind of craptastic. No, this one's not too bad. My low is at 5, and then my high, remember when it touches the edge of the graph, you assume it's an arrow going off to infinity. So my high value absolute is infinity, which is not a number. So we would say none for the max here. because that's what the note says. If you believe there is no maximum, type none. So N-O-N-E. But the low value appears to be 5. Now they could have given you like the flip where you have a max and then you don't have a min because it goes down to negative infinity. But that's the overall idea when you're looking at the graph. That makes sense on question 5? Is that what it was, like what the quandary was? Oh, you said 4.1. I'm looking at 4.5 like a damn fool. Ugh. The grump is, this is a math person attempting to write an application problem and sucking. So like the difficulty here is trying to understand what they said and then make sure what they said makes sense. Or do we have to do a what do we think they meant? All right, so we got an airplane flying overhead at a constant 4,010 feet. All right, so let's doodle our ground, doodle a little airplane. And they're telling us that this is 4010 feet. All right. A person is viewing the plane from a position 3,015 feet from the base of a radio tower. Oh, okay, so they like, it's kind of weird because you're like, where do I put the person? Where do I put the tower? Like, what does this have to do with the plane? You have to get all the way to the end. At what rate is the distance between the person and the plane increasing? Meh. When the plane passes over the radio tower. So we're gonna draw our weird tower under the plane. And now we're going to put the person 3,015 feet away from it. And then it tells us that the plane is flying away from the person at a rate of 650 feet per second. And then they say, at what rate is the distance between the person and the plane? All right, so we need to draw in person to the plane. And so they want to know the rate of change of this. All right, so I see a height distance. I see a horizontal distance. And then I see the diagonal distance. So the distance between the person and the plane is the rate of change of the hypotenuse here. This plane flying at 650 feet per second, this part's going to look a little weird, but that means that this horizontal distance is increasing at that speed. Because that plane is just that fixed height. So after a second, like the horizontal distance between them will be 3,015 plus 650. But we're freezing it at this 3,015 moment. All right. So what formula do I have that's going to relate these distances I'm talking about here? And you know what? Let's just label the sides. What do we want to call the height from the ground to the plane over here? It just needs a name. Yeah, we are going to use Pythagorean theorem, so X, Y, and Z works. All right, so we'll go with an X here, a Y down here, and a Z over here. So Pythagorean theorem, X squared plus Y squared equals Z squared. All right, is our X changing? The height of the plane? Nope. They told us, if we scroll back up, they actually used the word constant, and that wasn't just them trying to be verbose. So dx dt is 0. It does not change. Now dy dt is changing at 650 feet per second. And dz dt is the thing we're trying to find. So I can take my Pythagorean theorem here, differentiate with respect to time. So we're going to have d dt of x squared plus d dt of y squared equals d dt of z squared. All right, so what's our derivative of x squared? I know it's the Friday after Halloween. What do we do with x squared when we take the derivative? Yep. So it'd be 2x, 2 minus 1 is 1. And then because we're taking the derivative with respect to time, not x, we're going to get a chain rule with dx dt, which we know is 0, so that whole part's going to be 0. That's fine. Now here, y squared, same thing, 2y times dy dt equals 2z times dz dt. So this whole thing's going to be 0 because dx dt is 0. 2 times our y value is 3,015 feet. And our dy dt is 650. Then we have 2z dz dt. We need to know what z is. So we can just straight use the Pythagorean formula. Plug in x and y into the original equation and get z. Then we can use that in our differential equation and finish out and solve for dz dt. But does that help you see the setup and where to go from here? Because we are right at time. So I'm going to go ahead and, you're welcome. I'm going to go ahead and stop the recording.